December 1944, North Atlantic. Gale force winds exceeded 60 knots. Wave heights reached 50 feet. HMS Barfleur, battle-class destroyer, displaced 3,430 tons at full load. The ship rolled to port, 20 degrees. Standard heavy weather behavior, 30 degrees. Crew secured loose equipment, 35 degrees. Beyond safe operating limits for most destroyers, 40 degrees. Equipment broke free. The ship continued rolling. 42 degrees to port. Deck approached vertical. Water crashed over the bridge wing. Crew braced for capsizing. The ship hung suspended. 4.2 feet of metacentric height fought the laws of physics. Righting moment exceeded healing moment. Slowly, the destroyer rolled back. 30 degrees, 20 degrees, 10 degrees. Upright. No structural damage, no flooding, no system failures. The ship resumed station. 3 months later, American destroyers at Typhoon Cobra would capsize at lower roll angles. 3 ships lost, 790 men died. Battle-class destroyers operated in identical storms without loss. The design critics called top-heavy proved impossible to capsize. 1941, Admiralty faced contradictory requirements. Fleet destroyers needed 35 knot speed for screening capital ships, 8 21-inch torpedo tubes for surface engagement, heavy anti-aircraft armament against Luftwaffe and Japanese aircraft, anti-submarine weapons for convoy protection, radar systems for detection and fire control. Every requirement added weight above the waterline. Every ton added high in the ship reduced stability. Basic naval architecture: add weight above center of gravity. Metacentric height decreases. Metacentric height below 3 feet. Capsizing risk increases dramatically. Destroyers built in the 1930s prioritized speed and firepower. Stability came secondary. Tribal-class destroyers demonstrated the problem. Displacement 1,890 tons standard, 2,519 tons full load. Beam 36.5 feet, 8 4.7-inch guns in 4 twin mountings. Heavy firepower for destroyer. Metacentric height measured 3.1 feet at full load. Marginal stability. HMS Punjabi. Collision with battleship HMS King George V, May 1942. Ship capsized rapidly after bow damage. Insufficient stability reserve to survive flooding. HMS Cossack, torpedoed by U-boat U-563, October 1941. Remained afloat 24 hours. Capsized before reaching port. Better stability might have saved the ship. HMS Maori, bombed at Malta, February 1942. Capsized at dockside after bomb damage. Pattern emerged. Tribal class lacked stability margin to survive damage. J-class and K-class destroyers showed similar issues. J-class beam 35.8 feet. Metacentric height approximately 3.2 feet. Crew reported excessive rolling in Atlantic operations. K-class slightly better at 3.5 feet metacentric height. Still inadequate for heavy weather operations. Flower-class corvettes, excellent ocean-keeping vessels, rolled up to 45 degrees routinely. Crew became incapacitated. Combat effectiveness dropped to 0 during heavy weather. Royal Navy needed destroyers combining firepower, speed, and stability. Conventional design approaches failed to deliver all 3 simultaneously. Battle-class design began differently. Instead of starting with armament and fitting it into hull, designers started with required stability and built around it. Target metacentric height, 4 feet minimum. Unprecedented for destroyer with heavy armament. Achieving 4 feet metacentric height required fundamental rethinking. Beam increased to 40.25 feet. Tribal class beam, 36.5 feet. J-class beam, 35.8 feet. Battle class, 40.25 feet. 3.75 feet wider than tribal class. Nearly 5 feet wider than J-class. Wider beam increased hydrodynamic resistance. Maximum speed would decrease slightly. Trade accepted. Better to have stable ship at 35 knots than unstable ship at 36 knots. Armament selection focused on weight reduction. Conventional destroyer doctrine used separate weapons for surface and air targets. 4.7-inch guns for surface action, 4-inch guns for anti-aircraft. 2 gun types required 2 ammunition types, 2 handling systems, 2 fire control systems, 2 magazines, separate trained crews. Total system weight exceeded single dual-purpose system. Battle class adopted 4.5-inch Mark IV dual-purpose gun, 35-pound projectile, elevation -5 degrees to +80 degrees, surface range 19,600 yards, anti-aircraft ceiling 41,000 feet, rate of fire 20 rounds per minute per barrel, 2 twin mountings, 4 guns total, combined rate of fire 80 rounds per minute, equivalent firepower to 6-gun destroyer using separate systems, weight per twin mounting 30 tons, lighter than separate 4.7-inch and 4-inch mountings, top weight reduced significantly, fire control system integrated into single director, Admiralty, fire control table. Mark VI calculated firing solutions for surface and air targets. Type 2 8.5 surface search radar provided target detection. Type 2 9.3 target indication radar tracked aircraft. High-angle control system, director-controlled anti-aircraft fire. Low-angle director controlled surface fire. Single integrated system weighed less than separate surface and anti-aircraft systems. Further top weight reduction. Superstructure height reduced despite extensive electronics. Radar required multiple aerials. Type 2 8.5 needed height for surface search range. Type 2 9.3 needed clear field of view for aircraft tracking. High-frequency direction finding equipment needed elevated position. Operations room needed plotting tables, communications equipment, radar displays. Typical solution, build tall superstructure. Battle class designers integrated equipment into hull structure, operations room located below main deck, radar offices built into deck house rather than added above. Only essential aerials and directors remain topside. Result, lower center of gravity despite carrying more electronics than previous destroyer classes. Construction method changed. Pre-war destroyers used riveted construction. Overlapping plates joined by thousands of rivets. Heavy, labor-intensive. Welded construction joined plates edge to edge. Continuous weld seam instead of rivet lines. Weight savings approximately 8% of hull structure weight. Battle class displacement 2,325 tons standard. 8% of 2,325 equals 186 tons. 186 tons saved in hull structure. Weight available for equipment or retained as stability margin. Battle class used all welded construction for hull plating. Some riveting remained in high stress areas like machinery mounts. Primarily welded, significantly lighter than riveted equivalent. Fuel tank arrangement optimized for stability across operating conditions. Destroyers operate at various displacements. Full load, leaving port, 3,430 tons. Light load after extended patrol, perhaps 2,800 tons. 630 tons difference, primarily fuel consumption. Poor fuel tank design meant stability varied drastically. Full tanks, adequate stability. Empty tanks, dangerously unstable. Battle class fuel capacity, 790 tons. Tanks placed low in hull, centerline location. As fuel consumed during patrol, ballast tanks selectively filled to maintain weight distribution. Metacentric height remained above 4 feet throughout fuel consumption range. Calculated, tested, verified. First ship, HMS Barfleur, laid down October 28, 1942, at Swan Hunter and Wigham Richardson, Wallsend on Tyne. Launched November 1, 1943. Commissioned September 4, 1944, though not accepted into full service until November due to late delivery of fire control equipment. Inclining experiment conducted March 1944. Standard procedure measuring metacentric height. Ship heeled to known angle. Weight moved known distance. Heel angle measured. Calculation determines metacentric height. Result, 4.3 feet. Design target, 4 feet. Actual exceeded prediction. Sea trials, North Sea, March 1944. Rolled to 28 degrees in moderate seas. Recovered quickly without excessive pitching. Crew reported significantly better working conditions than Tribal class or J-class destroyers. Stability calculations proven correct. HMS Armada, second ship, completed April 1944. HMS Sance completed May 1944. HMS Camperdown completed June 1944. HMS Finisterre completed September 1944. Production accelerated. 6 British shipyards building simultaneously. Swan Hunter, Wallsend, John Brown and Company, Clydebank, Fairfield Shipbuilding, Govan, Camel Laird, Birkenhead, Hawthorne Leslie, Hebburn, Alexander Stephen and Sons, Glasgow. Total class planned, 24 ships. 19 completed during wartime, 5 completed post-war. Build time averaged 24 months per vessel. Slightly longer than previous classes. Increased beam required wider building slips. All welded construction required skilled welders. Time penalty accepted for stability gained. Final armament fit, 4 4.5-inch, Mark IV dual-purpose guns in 2 twin, Mark VI mountings, forward mounting, O position, after mounting, X position, mounting weight 30 tons each, elevation -5 degrees to +80 degrees, traverse rate 15 degrees per second, elevation rate 10 degrees per second, maximum surface range 19,600 yards at 45-degree elevation, maximum anti-aircraft ceiling 41,000 feet vertical, ammunition stowage 500 rounds per gun, 2,000 rounds total. Secondary armament, 2 single 40mm Bofors, Mark VII. 8 21-inch torpedo tubes in 2 quadruple Mark IX mountings. Depth charge capacity, 50 charges on 2 stern rails. Later ships fitted with 2 Squid III barreled anti-submarine mortars, replacing depth charges. Complement 232 officers and ratings. Larger than earlier destroyer classes. Additional crew required for radar operation, fire control, sonar, operations room plotting. Proper manning enabled proper operation. Before we see how these destroyers performed in the worst weather the Atlantic and Pacific could deliver, if you are enjoying this deep dive into Royal Navy engineering, consider subscribing. It helps the channel tremendously. December 1944. HMS Barfleur assigned Arctic convoy escort duty. Convoy RA-65, 40 merchant ships carrying war supplies to Soviet Union. 12 escorts, mix of destroyers, frigates, corvettes. Route, Loch U, Scotland to Murmansk, Soviet Union. Departed, December 15th. Weather deteriorated rapidly, December 17th. Barometric pressure dropped from 1,015 millibars to 980 millibars in 6 hours. Wind speed increased from 20 knots to 60 knots. Wave height built from 15 feet to 50 feet. Convoy scattered. Merchant ships struggled to maintain course. Escorts attempted to keep station. Barfleur stationed on convoy port quarter. Screening position against U-boat approach. Waves struck port beam. Ship began rolling. 20 degrees to port. Normal heavy weather rolling. 30 degrees. Crew secured all movable equipment. Galley shut down. Hot food impossible. 35 degrees. Approaching design limits for most destroyers. Engineering crew secured machinery. Fire room personnel lashed themselves to stations. 40 degrees. Charts broke loose in operations room. Radar operators struggled to maintain watch. 42 degrees to port. Extreme roll angle. Water crashed completely over port bridge wing. Deck vertical. Junior officers believed ship capsizing. Commander ordered no action. Nothing to do. Ship either capsizes or recovers, based on metacentric height alone. No human action affects physics at this point. 4.2 feet of metacentric height created righting moment. Distance between center of gravity and metacenter determined righting force. Longer distance, stronger force. 4.2 feet, strong righting moment. Heeling moment from wind and waves pushed ship over. Righting moment pushed ship upright. Forces balanced at 42 degrees. Then righting moment exceeded heeling moment. Ship began rolling back. 40 degrees, 35 degrees, 30 degrees, 20 degrees, 10 degrees. Upright. Roll duration approximately 8 seconds. Felt like eternity to crew. Post-roll inspection showed minor damage only. Broken dishes, loose equipment, charts scattered, no hull damage, no flooding, no structural failure. Ship resumed patrol station. Operations continued. Other convoy escorts reported damage. Tribal-class destroyer HMS Ashanti reported 40-degree roll with structural damage to forward superstructure. Plating buckled. Flower-class corvette HMS Bluebell rolled 45 degrees repeatedly, crew completely incapacitated by motion, unable to maintain watch, ship hove to until weather improved. Battle-class handling proved superior, wider beam, higher metacentric height, better seakeeping. Physics worked exactly as calculated. January 1945. Battle-class destroyers deployed to British Pacific Fleet, joined operations against Japan, different weather conditions, typhoons instead of North Atlantic gales, even more violent. June 1945, Typhoon Connie approached task force, British and American destroyers operating together. Wind speed 90 knots, wave height 60 feet, sea state beyond any Atlantic storm. American Fletcher-class destroyers reported roll angles exceeding 50 degrees. Several sustained hull damage, flooding in forward compartments, structural cracking. 3 months earlier, December 18 and 1944, Typhoon Cobra struck United States Third Fleet. Wind speed 115 knots. 3 Fletcher-class destroyers capsized. USS Hull capsized December 18th. Rolled beyond point of recovery. 202 men lost. USS Monaghan capsized December 18th. Roll angle exceeded 50 degrees. 256 men lost. USS Spence capsized December 18th. Rolled approximately 55 degrees based on survivor accounts. 317 men lost. Total casualties from Typhoon, 790 men. Cause insufficient stability at light displacement. Destroyers had consumed fuel. Weight distribution shifted. Metacentric height dropped below safe minimum. Heavy weather caused capsizing. Battle-class destroyers in same task forces experienced no stability issues. Maximum reported roll angle, 40 degrees during Typhoon Connie. No hull damage, no flooding, no structural failure. Fuel and ballast tank arrangement maintained metacentric height above 4 feet regardless of fuel state. American naval observers noted British destroyer stability. Several reports sent to Bureau of Ships recommending stability improvements for future destroyer classes. Battle-class design validated by surviving conditions that killed American destroyers. Comparison with Fletcher-class reveals design philosophy differences. Fletcher-class displacement 2,050 tons standard, 2,924 tons full load at maximum, beam 39.5 feet, length 376 feet 6 inches. Metacentric height 3.4 feet at full load, dropped to approximately 2.8 feet at light displacement after fuel consumption. Armament 5 5-inch 38 caliber dual-purpose guns in single mountings. 10 21-inch torpedo tubes in 2 quintuple mounts. 6 20mm anti-aircraft guns, later increased to 10. Speed 36.5 knots. Range 6,200 miles at 15 knots. Excellent endurance. Good firepower, speed advantage over battle class, marginal stability, especially at light displacement. 3 ships lost to Typhoon, multiple others damaged by heavy weather. Battle class displacement 2,325 tons standard, 3,430 tons full load, beam 40.25 feet, length 379 feet, metacentric height 4.2 feet at full load. Remained above 4 feet at light displacement due to ballast system. Armament 4 4.5-inch dual-purpose guns in twin mountings, 8 21-inch torpedo tubes in quadruple mounts, 2 40mm Bofors, speed 35.75 knots, range 4,400 miles at 20 knots. Similar firepower to Fletcher using twin mountings versus single. Slightly lower speed, significantly better stability. 0 losses to weather. Design philosophy, stability and survivability over maximum speed. German Type 1936. A destroyer, also called Narvik class, provides another comparison. Displacement 2,603 tons standard, 3,697 tons full load. Beam 39 feet, length 416 feet. Metacentric height estimated 3.2 feet based on surviving documents. Armament 5 5.9-inch guns in single mountings, 8 21-inch torpedo tubes, speed 36 knots, range 2,300 miles at 19 knots. Heavy guns created significant top weight. Poor fuel economy, limited range, questionable stability. German destroyer Z-29 capsized in Baltic Sea, February 1945 during storm. Roll angle at capsizing estimated 38 degrees based on survivor testimony. Z-31 sustained heavy damage from rolling same storm. Required dockyard repairs. German destroyers optimized for gun power and speed. Stability sacrificed. Several Narvik-class required ballast modifications after entering service. Design flawed from stability perspective. Soviet Ognavoy-class destroyers, contemporary design, displacement 2,240 tons standard, 3,110 tons full load. Beam 33 feet. Length 416 feet. Metacentric height approximately 3.5 feet. Armament 4 5.1-inch guns in single mountings, 8 21-inch torpedo tubes, speed 34 knots, range 2,600 miles at 20 knots. Narrow beam, severely limited stability. Soviet Northern Fleet reported multiple stability incidents. Several Ognavoy-class vessels restricted from operations in heavy weather Barents Sea. Design prioritized speed over seakeeping. Battle class operated Arctic without weather restrictions. British Tribal class provides internal comparison. Same Navy, same operational requirements, earlier design philosophy. Displacement 1,890 tons standard, 2,519 tons full load. Beam 36.5 feet, length 377 feet, metacentric height 3.1 feet. Armament 8 4.7-inch guns in 4 twin mountings, 4 21-inch torpedo tubes, speed 36 knots, range 5,700 miles at 15 knots. Heavy gun armament for destroyer, created excessive top weight, stability marginal, HMS Punjabi collision damage. May 1942 caused rapid capsizing, HMS Cossack torpedo damage. October 1941 capsized before reaching port. Insufficient stability reserve to survive battle damage. Tribal class demonstrated cost of prioritizing firepower over stability. Battle class learned lesson. Beam increased. Metacentric height prioritized. Result: 0 battle class lost to stability failure. Combat service proved design effectiveness beyond stability. Battle class entered fleet service 1944. Too late for Atlantic convoy battles. Primary deployment British Pacific Fleet 1945. Operations against Japanese home islands, shore bombardment, carrier screen, radar picket duty, HMS Barfleur, bombardment operations, Sakishima, Gunto, April through May 1945. Fired 1,200 4.5-inch rounds at Japanese positions. Destroyed multiple shore installations, no gun jams, no mechanical failures. 4.5-inch dual-purpose guns proved reliable under sustained fire. HMS Armada, anti-aircraft defense during kamikaze attacks, May 1945. Shot down 2 kamikaze aircraft using 4.5-inch guns at high angle. Dual-purpose capability validated in combat. HMS Sant, radar picket duty, detected Japanese aircraft formations at 50 miles range. Type 285 radar effective. Provided early warning allowing carrier combat air patrols to intercept. All battle-class vessels, Pacific operations, 0 lost to enemy action, 0 lost to weather, 0 lost to mechanical failure. Design robust, reliable, effective. Post-war service demonstrated design longevity. Most wartime destroyers scrapped by 1960. Battle class remained active Royal Navy service through 1975. 30 years operational life. Exceptional for destroyer design. HMS Agincourt served until 1974. HMS Aisne served until 1970. HMS Barfleur served until 1966. HMS Cadiz served until 1967. Design robustness allowed extended service. Several converted to radar picket destroyers, 1950s. Additional radar equipment added. Large aerials mounted on lattice masts. Top weight increased. Original 4.2 feet metacentric height provided margin accommodating modifications. Stability reserve designed into original specification enabled modernization. Royal Australian Navy purchased 8 battle-class destroyers between 1948 and 1958. HMAS Anzac, HMAS Tobruk, HMAS Bataan, HMAS Arunta, HMAS Warramunga, HMAS Vendetta, HMAS Vampire, HMAS Duchess. Operated until 1977, Australian service-validated design in different operational environment. Tropical waters, Indian Ocean monsoons, Southeast Asian operations, HMAS Anzac, Korean War Service, 1950 to 1953, shore bombardment operations, HMAS Tobruk, Vietnam War Service, naval gunfire support. Battle class proved adaptable across multiple conflicts, climates, decades. International adoption demonstrated confidence in design. Cost analysis shows value despite higher initial expense. Build cost per vessel approximately £1,200,000, 1944 prices. Fletcher class build cost approximately $700,000 United States dollars, roughly £300,000 equivalent. Battle class cost 4 times more initially. Service life battle class 30 years average. Service life Fletcher class 20 years average. Cost per year service battle class £40,000, Fletcher class £15,000. Initial cost higher, operational value superior. Stability meant fewer weather restrictions. Destroyers available for operations year-round. Reliability meant higher readiness rates. Longevity meant no replacement procurement for 3 decades. Total life cycle cost favored battle class despite higher acquisition expense. Strategic impact extended beyond individual ships. Battle class demonstrated wide beam, high metacentric height philosophy worked. Influenced all subsequent Royal Navy destroyer designs. Daring class destroyers, first class post-war, displacement 2,800 tons standard. Beam 43 feet. Metacentric height 4.5 feet. Battle class principles applied. County class guided missile destroyers, 1960s design, incorporated battle class stability standards. Type 42 destroyers, 1970s, maintained emphasis on stability. Modern Type 45 destroyers trace design philosophy to battle class. Stability as primary requirement, not afterthought. 42-degree roll North Atlantic. December 1944 changed British destroyer design permanently. Crew testimony validates theoretical performance. Lieutenant Commander J.R. Gower, Commanding Officer HMS Barfleur, Action Report, January 1945. Quote, "Ship handled heavy weather superior to any destroyer previous service." End quote. Specifically noted, crew maintained effectiveness during conditions incapacitating crews on narrower destroyers. Engineering department reports indicated stable platform permitted machinery maintenance during rough seas, impossible on earlier classes. Gunnery officers reported fire control solutions remained accurate despite rolling. Radar operators reported equipment functional throughout extreme weather. Stability translated directly to combat capability, not abstract engineering parameter. Real operational advantage. Post-war German naval analysis examined Allied destroyer designs. German documents captured by Allied technical teams included battle class assessment. Kriegsmarine engineers noted beam-to-length ratio, noted metacentric height calculations, noted stability at light displacement. German conclusions: British wide beam approach superior to German narrow beam. High-speed philosophy. Multiple Type 1936 and Type 1936. A destroyers lost or damaged by weather during war. Battle class lost 0. German engineering culture acknowledged British design superiority. Rare admission. American destroyer development incorporated battle class lessons. Gearing class destroyers. Wartime design completed 1945 through 1946. Increased beam to 40.9 feet. Metacentric height improved to 3.8 feet. Still below battle class 4.2 feet, but significant improvement over Fletcher class. Sumner class destroyers, immediate Fletcher predecessor, experienced stability problems. Gearing class modifications addressed issues. United States Navy technical missions visited British shipyards post-war, studied battle class construction. Post-war American destroyer designs, Forrest Sherman class and later, prioritized stability more heavily than wartime classes. Battle class influenced global destroyer development. Soviet Navy obtained German technical documentation, including battle-class analysis, through captured archives. Post-war Soviet destroyer designs showed increased beam. Skory class, 1949 design, beam 39.3 feet. Improvement over Ognavoy, 33 feet. Kotlin class, 1954 design, beam 40.2 feet. Matches battle class exactly. Soviet designs converged toward British stability principles, never publicly acknowledged, documented in design specifications. December 1944, 42-degree roll validated 4 years engineering work. Naval architects calculated 4 feet metacentric height required. Shipbuilders increased beam to 40.25 feet. Designers reduced top weight through dual-purpose guns. Welded construction saved weight. Fuel tank arrangement maintained stability across displacement range. All calculations tested sea trials. All predictions confirmed combat operations. Critics argued design too wide. Critics argued dual-purpose guns, insufficient firepower. Critics argued top-heavy. 4.2 feet metacentric height proved critics wrong. Battle class survived weather-sinking other navies' destroyers. 24 ships built, 0 lost to weather, 0 lost to stability failure. 30-year service life. 8 ships sold Australia, demonstrating international confidence. British destroyer design philosophy changed permanently. Beam became priority. Metacentric height became requirement, not goal. Subsequent classes incorporated lessons. Fletcher-class destroyers capsized Typhoon Cobra, December 1944. 3 ships lost. 790 men died. Inadequate metacentric height at light displacement. Narvik-class destroyer Z-29 capsized Baltic Sea, February 1945. 38-degree roll angle. Insufficient stability. Battle-class destroyers rolled 42 degrees North Atlantic, 40 degrees Pacific typhoons. Came back every time. Engineering calculations proved accurate. Design philosophy proved correct. Physical testing proved capability. Combat operations proved reliability. British naval architecture excellence validated not through theory, but through performance. Not through claims, but through survival. Not through specifications, but through 0 losses. The destroyer, everyone called top-heavy, demonstrated superior stability. The design skeptics criticized proved impossible to capsize. The ships that rolled 42 degrees kept fighting. Innovation driven by operational requirements, stability achieved through calculation and testing, superiority proven through 30 years service, battle-class destroyers, 42 degrees and still afloat.